Hello. This is the first episode of Poincare's Insights, Maths podcast, based in London. I'm your host, Sujay Meedum, and this is my co-host, John.
Hi, my name is Dylan Shah, and I currently study A-level maths and further maths with your host Sujay right here. And yeah,
It's here. And the main idea of the podcast is we're here to talk about mathematical theories, and in later episodes, we're going to talk with Cambridge students and hopefully some professors if we can get them on. Well, Dylan, my first question to you is, have you heard any interesting math theories over the weekend?
over the weekend,
We
well,
just started.
I've certainly heard like some crazy theories over my life, or like theories that just like keep me up at night. Like I started reading this book, Infinite Powers by Stephen Strogatz. I don't know if you've heard of it, but it's basically like he tries to talk about the depths of like calculus and all that, how important calculus is in like the real world, and then he tries to explain calculus using infinity and all of that. And uh, there's one part in the book where he starts talking about Zeno's paradox.
Oh,
So I
okay.
don't know if you heard about Zeno's paradox,
I
but
think
that
I've I
is
think I've just about heard of it.
yeah, it's like a paradox to do with infinity. It's like okay, I'll lay out the paradox for you. So basically, say you have two runners, yeah. You have a let's just say you have like a slow moving runner like a tortoise or something, and you have a sprinter, yeah. And
Yeah.
the theory goes that the paradox goes that if you like put the slow runner with a head start, like give them a head start, and you start a race between the slow runner and the fast runner, the fast runner will never be able to catch up with the slow runner because like every time it's confusing. Even like I don't know, I'm like the surely the fast runner will be able to catch up with the slow runner at some point and overtake, right?
Yeah,
But
surely.
the explanation is every time the slow runner takes a step, yeah,
Yeah.
it takes the fast runner also takes a step, but like the the magnitude of their steps are like incomparable. So let's say that the fast runner step will be way quicker than the slow runner step, but they've both still taken steps forward. So by the
Yeah.
time the fast runner is caught up to where the slow runner was, the slow runner has moved a tiny bit more forward, and it'll keep on going like that, eventually to the
Until
point like
infinity.
till
Yeah.
infinity. Like
Yeah.
literally, the fast runner will never be able to catch up to the slow runner, and that just like keeps me up at night. Like I don't know how to explain it. It's like my brain melts. I I don't know how it works, but yeah, it's some crazy like paradox.
Fair enough. Fair enough. I've
What about
I,
you?
I recently also I think someone in our school also like asked me a question while I was just in the common room after working. They were like, so they had three doors. It's a problem for like a movie. It was like a movie called 21, but maths and like blackjack.
Mm. Oh
How
yeah,
math
yeah.
applies to the
I've
real
watched that.
world. So it's like three
Yeah,
doors, and then like let's say I choose a door, and like behind them there's like two goats and a car, and like let's say I
yeah.
choose door number three, and he opens door number two, and there's a goat behind it, and
Mm.
he asked me, can I switch my choice? And I say yeah because of variable change. It doesn't really make sense to start because um, when they asked me, like, wait, doesn't the probability just split and go to 50-50 then? And I said,
Mm.
well, not really, because, like, imagine, like, you lock in your choice. So you no longer have the option to change the probability of that. Since originally, between all of them, you had 33.3%.
Yeah,
So
yeah.
one of them you've chosen has 33.3%. But now, since you've taken one away, the 33.3% that you had from door two can go to door one now. So in
Mm.
terms of maths, I'd always change and go to door one, which kind of doesn't make sense in a way because you normally expect, even anyway, that the probability would split.
Mm.
I think it's called the Monty Hall problem when I searched it up last ever. It was kind of weird though. Like maths is it's kind of
Yeah,
weird to explain
probability
how
and all
maths
that. It's a
works.
bit buggy. You can't trust probability.
It never can. It's always a hard problem, even in the MAT.
Oh, the MAT, bro. The
Yeah.
MAT is actually like I don't know. It's kind of hard to explain the MAT because like you feel you feel that the more you like practice, the better you get. But the more you practice, the more you stumble across, and then the more like you become like confused and all that. It's
Yeah,
hard to
because the
practice them
problems
if you.
are just AS level, which doesn't really make sense. Like you should think
Yeah,
less content, so it should be easier. The questions are always just hard when you think
out
about
of
them
this world.
properly.
It's crazy.
Anyway, any more interesting theories? I've been reading a little bit into your personal statement, seeing some
Oh
Simpson
yeah,
paradox.
Simpsons paradox. That actually relates to your the other paradox, the other theory you're just talking about. It's like you know how you said, oh, with statistics and probability, like it may not like whatever's on the surface may not be true. Yeah, it's
Oh,
basically
okay.
the same thing with the Simpsons paradox. It's like if you take two variables, okay, let's take two stats. Yeah, I'll give you like an example. Say you have like an ill relative and you need to take them to an hospital. Yeah, you have hospital A, hospital B. Hospital A has like a, let's say, 80% chance of survival, and hospital B only has like 40% chance. Yeah.
Yeah,
So like at first you'd say, oh, hospital A, surely like we should take them to hospital A.
yeah,
But the thing is, if you divide each hospital into further like stats or like further variables, stuff like the age of the people that entered the hospital at first and all of that, you would see that
yeah.
hospital A had more older people that like were admitted to the hospital, and therefore like sorry, I mean hospital B had more older people, therefore they had a lower like mortality rate and all that.
Oh,
So
yeah.
so you have to
Okay.
take into account like other variables to see which one like would be better.
Okay, so showing the truth behind different variables, you can't always trust certain numbers. Fair enough. Yeah.
Yeah, exactly. Yeah.
That's similar to another theory. But this always links with theories in maths. Like I've heard another one called Bertrand's paradox. It kind of
Mm,
talks about the truth behind like certain words in maths. So like a question can say like um, between these values or like have an inequality sign, but like there's always some doubt with that. Like why does that necessarily have to work? Or like a different part, like it will say like look at this scenario, but what does that really mean? And it questions like
mm,
the wordiness of maths technically, like how can you word a problem to make absolute sense in a way?
mm. Wait, Sergio, one second. I have to go for a bit, but I'll be back. Just like
Okay, I'll
two,
pause the
three
recording.
minutes. Yeah, pause the. All
Yeah,
right, Sergey, I've been reading your personal statement too, and
uh,
I saw something like Zone's lemma or something like that. I didn't really like understand what it was properly. So like, if you could like enlighten me on what this is.
that's fair enough. I think I heard from someone it's like a Cambridge third year topic, and like you don't really learn about it.
Oh,
It's like advanced set theory. It's really long. As in,
whoa,
like, the basic idea is it's just like the same thing as the axiom of choice. The axiom of choice
mm,
is like, and like all axioms in math like form like Lego layers, like it's the base layer of all of maths.
foundation, yeah.
It's just foundations of maths, and like axiom of choice is like used to be like a heavily argued idea. Like people weren't really like, let's just say they were really reluctant to introduce a new idea into maths.
Mm,
And like axiom of choice to say is like, let's say like there's a bunch of non-empty finite sets, like just a bunch of like sets in there, and you can choose an element in each of them and
mm,
create an entirely new set. That should just be simple, right? Like I can choose an element in each, like let's say I have 10 boxes. I can choose
yeah.
an element out of, I can choose one element out of each box and create a new box.
Okay.
Yeah, that should normally just like work, but like
Yeah, yeah.
many people just argued over it. It was just kind of weird. There could be like contradictions to it as well.
Mm,
And Zorn's lemma, like I'll read out the definition first. It says, let P be a partially ordered set such that every chain has an upper bound in P. Then the set P contains at least one maximal element. Now, none of that makes sense to you at the start because
that
you don't know
is,
what partially ordered set is.
yeah.
You don't know what
No.
chain is and P is. Yeah, it's kind of weird.
No.
Uh, well, like obviously the first part of the definition is partially ordered sets. So I'll go through
Mm,
this first then, partially ordered sets. Partial ordered sets are like any other sets. Like they just have
mm,
certain rules to them though. So there are four main rules. One is that they're reflexive. Like everything in the set is related to each other. So
Mm.
let's say like you have A in the set X. Um, A is related to another element, and that's just basically what it's saying. Like all of them have some relation to each other.
Mm.
And then the next one is anti-symmetry. It just says
Okay.
like if A relates to B, then B relates to A. It's
Okay.
kind of
Yeah.
saying the same thing. It's just saying like,
Yeah.
okay, as in the first example says like A relates to A. That's just showing like the
Mm-hmm.
element is itself. The second one
Mm.
showing that two different elements can just be like swapped, like in multiplication how they're like how numbers can be swapped, like 2 times 3 is 3 times
Oh
2.
yeah. Yeah.
The
Yeah. Two
same
times
idea
two. Times two.
basically.
Yeah.
And then another one is transitive, which is like if A relates to B and B relates to C, then A should relate to C.
Should. Yeah. Okay.
Yeah,
Yeah.
it should. And that just defines a partial order sets. And those main ideas are kind of needed to explain further, like what Zorn's lemma is.
Mm.
So like I also use like a thing called Hasse diagrams to explain it. So let's say like I have a bunch of circles that like
Mm.
and an element in the set X. So let's say I have 1, 2, 3, 4 in the element in the set X, and I draw circles around each of them. So circle around one, circle around two,
Two.
so
Three.
on.
Yeah. Okay.
And a Hasse diagram just shows like the connection between each of the elements. Because remember
Mm-hmm.
when I talked about partial order sets, I said everything's related to each other, the
Mm.
first law, and the Hasse diagram just sort of represents that. And through that Hasse diagram, I can say there's a maximal element. Now, I'll let you try and guess what maximal element is. Go on, try and guess it.
Nah. No. 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 Whoa. 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 You just put me on the spot
Uh,
there.
like a maximum element is not like the maximum element. It's not the biggest number in the set. It's just like you
Yeah.
can,
That's exactly what I was thinking though.
yeah, it's not that. It's really confusing. It's just like an element within the set you let be the maximum. So like let's say I have 1, 2, 3, 4 again. I can let
Mm.
3 be the maximal element.
Also, you choose.
I can choose. That's the point. Like you can see the similarity between axiom and choice now.
Yeah.
Like I can choose that as that.
Mm.
And then
Mm-hmm.
now like since I have that maximum element, I can say that there's like nothing above that, technically.
Mm.
Like in terms of the set, I have nothing above that. And like with definition it says then set P contains at least one maximal element. And that's true. And every chain has an upper bound. In Hasse diagrams,
Okay.
they draw the connections.
Yeah. Yeah.
They all can relate to the central three I told you about. Like let's say I took three as the example. So
Mm-hmm.
1, 2, 3, 4, and I took three as my upper bound. I can link
Yeah.
all of them by drawing chains to
Mm.
three, and that just shows like,
Oh. Yeah.
oh,
Okay.
I created like a new set with three in
Mm-hmm.
there as my center because I can choose four as my center. I can choose one as my center, or I can choose two as
Yeah.
my center, and I technically create four different sets because each of them are new maximum elements, if that makes sense.
Mm-hmm.
And that just shows like the new relationship between like advanced set theory, like something you wouldn't imagine to talk about necessarily, and like normal, just like basic ideas, like the axiom of choice.
That's crazy.
That was a
That is
long
a
talk.
lot to take in. That is a lot to take in. Whoa.
Like to be honest, none of it made sense at the start. Like I had to watch about like seven different videos, and then like it goes into functional analysis and like different things like metric spaces and all of that. And it's like just different concepts of maths that you think have no relation to the world, but like
Mm.
it's very necessary since like the axiom of choice is a fundamental thing. Even that advanced set theory of Zorn's lemma is technically the fundamental of maths, I can say,
Mm-hmm.
and it just shows like how everything can link, just in general. That was a lot of talking for me, so
That is crazy.
yeah.
Well, I don't know what to say. My mind's like all over the place right now. I guess after this pod, I'm just gonna have to go and research like you did.
Fair enough.
Oh, it's crazy. I mean, yeah, it's really interesting though. But
That's
yeah.
cool. Anyway, I guess any more paradoxes from you? You seem like a paradox merchant.
Paradoxes. I mean, I don't really have like a paradox I want to talk about, but I do have like a cool, like fun maths fact, I guess, if you
Yeah,
want.
go on.
So
Let's
like
hear it.
basically it's have you heard of Euler's characteristic formula?
No, as in like I know
Right.
of Euler, like the mathematician.
Yeah. So yeah, he has like a characteristic formula to do. It's like it's kind of like a geometry fact. So basically, say you take just a plane, you have like a normal plane, yeah, and okay, wait, let me just tell you the formula. The formula goes like this, yeah. The number of vertices take away the number of edges is equal to the number of regions on a plane. Now, like at first, like it doesn't make sense, but like what do you mean by vertices, edges? But like,
Yeah.
let me just explain now. So just take a plane and let's just take like a shape like a triangle. Let's take a triangle, yeah. The triangle has three vertices, yeah, and three edges. And the number of regions in this plane for the triangle is just the inside region and the region outside it, yeah. So if we take vertices, take away the edges, um, plus the regions, we would get three take away three plus two, which is equal to two, right?
Oh,
Now
yeah.
the thing is, yeah, this formula will always equal to two. So so let's take the triangle again, yeah, and split it down the middle. Yeah.
Yeah.
So now you've got one, two, three edges, and now you've got another edge down the middle, so four.
Yeah.
And you've also got another vertex here. Even though it's like straight,
Yeah.
there's still a vertex
It's
here connecting the edge.
yeah.
So now you've got four edges, four vertices, and now you've got one region here, another region here, and the outside region because this got split down the
Yeah.
middle. Yeah. So one, two, three, four. Yeah.
Yeah.
Four four edges.
Edges and
Take away take away the vertices. One, two, three, four.
yeah.
Wait, wait, I think I messed this up. I think I
Confused
messed this
yourself.
up.
It's
No,
all
but
good.
like, yeah, I think I messed up. The point is, if you just like take this formula and apply it to any like geometry shape, even if there's like overlapping lines and all that, if you take the number of edges and vertices, add them together, and take away the amount of regions, you'll always get two, which is like crazy. I don't know why it's always two, but it's just a fact. It's just like an
Yeah,
identity,
fair
I
enough.
guess.
I mean, you did get confused yourself, so
Yeah, I got confused while explaining it. That just shows like it's crazy.
as in, like, clearly maths is like just a confusing thing. Like, I was reading a book called Is God a Mathematician?" It's in my personal statement as well.
Oh yeah,
I've
yeah,
read
yeah,
about it. You've seen it probably. And then
yeah.
like it was talks about like obviously like is maths like created by us humans or is it like found by us? Like, is it created by like God or something?
Hmm.
And like, surely if it's created by us humans, we should all technically like understand it to a certain extent, even if it's confusing to us. But like, I at least personally think it's just like found by us. Like, I think Plato's cave was an example that he talked about in his book. Like, I think you've heard of Plato, right? The Greek
Yeah, Plato.
philosopher and
Yeah.
mathematician. Yeah, it's a famous guy. Don't ever know what he did. Yeah, but like he thought of maths as like us humans at the back of a cave, and there's
Hmm.
like light entering the cave, and we're always just like crawling towards that light because we don't know like the extent of mathematics, like the incompleteness of mathematics, and like it's just vast array in general. Like it's such a big
Hmm.
topic, and it like defines like a lot of humanity. Like roller coasters that we have fun on, we don't really think about it, but it's all
Yeah.
mathematical and physics. Like I mean, like what I don't personally think I remember a time when I thought about circular motion on the top of a roller coaster going on a loop ever in my life. So I don't think that's possibly ever happened. Like S minus mg squared of r. Yes, that's definitely right. Uh,
Oh,
yeah,
that's cool.
generally it was going through like the history of maths, like from Euclidean axioms, like the basis of maths, to like
Hmm.
non-Euclidean geometry, Galileo, and then like famous like Gödel, like Gödel's incompleteness theorem, all of
Oh
that
yeah, yeah,
stuff.
yeah.
Uh, that's like, yeah, that's basically what we've done so far. As in, we do have our exams soon. about 4 days. About four
Oh
days,
yeah,
yeah.
the math exam.
My exam.
Yeah, the math exam. That is scary. That
Yeah.
is really scary. Because I think three of my unis need it right now. And like three of my unis look at it. So
I think only one of my unis, Imperial, looks at it. I think Warwick also stepped, personally.
oh yeah, Warwick kind of also step, but they take either.
Yeah, they do. So
So
it's
yeah.
fine.
Mm.
There was a little break in between. So I think Dylan's come back with a corrected version of his.
Yes. Okay. Yeah. So okay, let's go back. Yeah. So you got your triangle, yeah, and you split it down the middle.
Yeah.
So now you've got how many vertices have you got? One, two,
Two, three,
three, four.
four. Yeah.
Four, right? All right. And the formula goes, wait, sorry, I just saw the formula. The formula goes vertices take away edges. So you've got four vertices and you've got one, two, three, four, and then one edge going down the middle. So
Oh,
five.
you forgot the, yeah.
Yeah. So four take away five, that's minus one. And then you add up the regions. So one, two, and then the outside region, three. And that minus one plus three, two. So you can like divide it into how many ways you want. You can do it like overlapping stuff and all of that, as long as you count each edge like in between two vertices, and then it'll always add up to two, which is like crazy. But yeah,
Yeah.
okay, I
Oh, I
finally
see it.
solved it.
Yeah. Now it
I was bugging
works.
out before. I was bugging out before, but it can work.
Now
It
it
doesn't
works.
even like it doesn't even have to be a triangle. It could be like a parallel. It's a
Parallelogram.
circle. Yeah, a circle, or anything, literally,
Fine.
a diamond, anything you want.
That's cool.
But yeah,
Uh,
so Jay, I have a question to ask you.
oh no, not again. Let's go for it.
What is it's a generic question. It's not that hard, but what is your favorite part of maths? It's so like it's in such a like a vague question. You can answer it however you want.
What's my favorite part of maths? I mean, I would have said algebra just for the easiness, but I guess the most interesting part of maths for me is, I guess, like metric spaces. Like they weren't like they. I think it's first year or second year uni you come across metric spaces initially.
Mm.
It just like so. Let's say I have a set X. It's another set one. You need to think about sets a bit. This one,
You
yeah,
love sets, man.
I
You
really do
love
love
sets.
sets. So like, let's say there's a set like E, and there's two elements X and Y
Mm.
in there. I can find the distance between those two elements if
Okay.
they obey certain laws. So one main thing I came across, like especially after doing the UKMT, like I used to struggle with inequalities a lot. And like I
Mm.
bought a book on like inequalities from the UKMT website. And like I found this one called triangle inequality. It was weird. Like it's normal though. Like it says like let's say you have a triangle. You have like the distance the distance of like x plus y is
Yeah.
always greater than the distance of the hypotenuse. Like
Right.
that always makes sense. Like as in like I was walking through my park once, like and I clocked it and it was so cold. Like my park just like has a path where you can just like go through, cut across, like the
Mm.
hypotenuse. And like normally I just go across and go through that way. But once I went this way and I thought, wait, that's faster. I thought I was a genius. Yeah. It's just some like real life examples of like you wouldn't really clock that normally. I don't know why I was
Mm.
thinking about the triangle inequality then.
No, well, yeah, I guess that kind of relates to like my favorite part of maths, just like the reality of maths, just like real life examples that you can like
Yeah, as
pair
in
with
like the way
maths.
you clock maths differently
Yeah,
sometimes.
literally, like anything applied maths is just so cool. It's like mechanic, especially mechanics. It's just like, oh, if I bounce this ball from here, surely it'll come back to the same position, right? But no,
No,
no.
no,
Coefficient of
can't.
restitution, no.
Friction can't do that.
Yeah, so it's just like, like wait, did I just tell you that like about dropping the ball and all that? Yeah,
Yeah, drop
so
ball, coefficient
just yeah,
restitution,
coefficient
all that.
restitution, all that. So it's just like the reality of maths, like how much we can actually relate to it because it happens in real life too. It's just so cool. That's why I like applied maths the most. It's just my favorite part. But
No,
yeah,
the problem is I don't like doing the applied maths like in general. Like I just don't like writing that down. Like Suva, I've not bothered with that. I
see
don't like
that.
solving pure maths, but if pure maths relates to the real world, it's cold. Like I think
Mm,
one thing I read in the Is God a Mathematician's book is that I don't think you've learned we've covered hyperbolic functions in school yet. We're gonna cover it in Corpio 2 further maths. So
mm.
like there's chains in London. You have those like two black poles and you have that black chain there. Crosses it. Yeah. So there's two poles and then you have the black chain in London. Like if you ever like walk around, you've sometimes seen those. Like that curve is a Koch curve. Like a Koch curve is just like a really like extended version of like an x squared curve. But like that curve is always a Koch curve. Like in nature, it carries the least potential energy. And like
Oh,
you would never think about like Koch curves in general, but like after I watched a video on it, or like I read it on the book and then I watched the video, it made so much sense. Like nature like has so much maths in it you wouldn't realize normally. Like why does it have the least potential energy and why is it that special curve? Like it's just weird. You would never think about it.
yeah, true. And like going back to like the thing you just said about Suva, you hate Suva, right? And
Yeah.
I just remembered like I was thinking about Suva and I met up with my friend from Kenya the other day and I was like, oh, I'm gonna go home and do Suvat, like as a joke. Yeah. He's like, what do you mean Suvat? And I said, oh,
Oh,
like velocity, initial velocity, final velocity, displacement, all that. He's like, oh, what? You mean Vutos? And
Vuitton.
it just got
Oh,
yeah, it's in Kenya they learn it as Vutos, and it just got me thinking like maybe this is like another topic for another pod, but like how maths is taught differently around the world.
Oh, that's actually interesting. I've never really considered it because like I've been to India, sure, but like I've never really like asked them about like the learning technically, and I see how it can be
Yeah,
different.
yeah, exactly. So like it's just something to think about, like the way maths is just taught differently around the world. Like if it has like an effect on anything really. But yeah, maybe that's like a topic for another
Yeah.
day.
Cool. I think we're nearing the end of the podcast, as in we've talked about quite a lot. We covered quite a variety of topics. Both me and Dylan have explained quite a bit, I'd say. Um, to sum of the podcasting going next week, the next week's podcast is us with a Cambridge student. He's third year, and his name's Will Templeton. He's Gonville and House College, I think, and like he's extremely smart. To be honest, he's like 90 in MAT. He's got like British Maths Olympiads awards. He's really intelligent, to be honest. He knows about a lot about maths more than us. I think he can explain a variety of topics greater than us. I think I've asked him to go through group theory in special detail because it's something that can come up in interviews. So it will be
Mm,
a little nice thing to go through. And then yeah, we'll see how that goes. Basically, that's Poincare's insights for you. Me and Dylan, Dylan's a co-host, but Cav is also a co-host. He might come on later. He's currently extremely hardly revising for the MAT. And then, yeah, that's basically it. See you. Bye, I guess.
all
Bye.
right, thank you. Bye.
Thank you. Bye.